basic difference between the one-way slab and two-way slab is that in one-way slab, the ratio between the longer span by shorter span is more than 2. Means it is more in length. The longitudinal length is more than the twice of the breadth. Okay. In two-way slab, you will see that the shorter span and the longer span are near about similar. Okay. So the ratio of the longer span by shorter span you will find is less than equal to 2. This is the basic definition of the one-way slab and two-way slab both. The definition of one-way slab is that it is a slab, where the ratio of the longer span by shorter span is more than 2. Okay. So from here what you can see that the bending that is happening is more prominent in one direction. Okay, that is along the shorter direction. If you see, compare the bending of these two slabs. At the center of the slab, you will find that the bending is constant for both the shorter span and longer span. Okay. But when you see from one end, okay, along the shorter span, you will see that the bending here is more compared to the longer span. Okay. Whereas for your two-way slab, the distribution of the bending moment is quite similar for longer span and shorter span. Okay, because they are distributed equally, so the bending is quite equal between the shorter span and longer span. Unlike your one-way slab, where the bending you will find is happening more, means the curvature, okay, the curvature of the radius of the how much it is bending, okay, the radius of the curvature is, you will find that it is less for the shorter span and more for your longer span. Okay, so for this reason we will have to provide the main reinforcement in the shorter direction for one-way slab. Okay. Reduce the bending, we have to provide reinforcements in both the direction, in shorter span as well as in the longer span. So to reduce the maximum bending moment, which is generally acting on the one-way slab, is in the shorter direction. So that is why the main reinforcement, okay, these are the main reinforcement or primary reinforcement. These reinforcements are provided on the shorter direction. Main reinforcement, main bar or primary reinforcement जो बोल सकते हो. Okay, and in case of this bar which is along the longer direction, you will find they are called your distribution bar. Okay, they hardly pays for your bending moment hardly raised. Main resistance of the bending moment is taken care by the primary bars, by the main reinforcement. They are called distribution bar. Okay. In this case, for your two-way slab, you will find since both the directions are carrying the almost equal amount of bending moment, so both the direction reinforcement, x and y direction reinforcement are similar. Okay, the importance is similar. So one is your primary. Another direction, in the y direction, it is secondary. slab, since both the primary and secondary bars are taking care of the bending, okay, are acting because of the span equal span, they are carrying same equal amount of bending moment. So that is why there will be lesser deflection compared to your one-way slab, where since due to maximum in the longer direction, it is because of the length, the maximum bending is coming on the shorter direction. So only one reinforcement, only one type of reinforcement, one direction, primary reinforcement is acting for resistance of bending moment, okay, along the shorter direction. So that is why bending here is more compared to in your one-way slab. Okay, so in two-way slab, in one-way slab, in your one-way slab, we have span longer. Okay, the longer span is more than twice of that of the shorter span. So that is why the dependency on the resistance of the bending is totally carried by the main reinforcement. Okay, so that is why their bending is comparatively more. Okay, because only one direction reinforcement is taking care of the bending moment. So that is why the depth of this type of slab you will find is more, or the reinforcement requirement is also more compared to your two-way slab. Okay, and in your one-way slab, the function of the distribution bar is mostly to take care of the holding the primary reinforcement. Okay, the purpose of the distribution reinforcement is to make sure that the primary reinforcement are in position. Okay, there is equal distribution along the main reinforcement. Okay, this is the purpose of the distribution bar. But with the two-way slab, both the primary reinforcement and secondary reinforcement are taking care of the bending. Okay, both are acting for restricting the bending. Okay, for restricting the deflection. Okay, this is the basic difference between the one-way slab and two-way slab. Okay, first this one is the basic difference, the length. Okay, second, the reinforcement type of reinforcement that we are carrying. It is the bending is carried on the shorter span, so the reinforcement is provided. Main reinforcement is provided along the shorter span. Okay, but in case of two-way slab, in both the directions, both in shorter span and longer span, the reinforcements are provided, which are main reinforcement and secondary reinforcements are provided, and both are acting for resisting the bending moment. Okay, this one is less economical because the depth of the slab will be more, because it is carrying more bending in one direction, deflection is more, and whereas since it is equally distributed among the secondary bar and primary bar, the deflection is less, so it is more economical. These are some of the basic difference between the one-way slab and two-way slab. Okay, understood? The effective span has been discussed. Next part is your deflection. Okay, how to restrict the deflection. But in how many ways we can resist the maximum deflection? Okay, so to resist the maximum deflection, or the criteria for deflection, as you know, that is common for your beam and slab. Okay, so what is the criteria that is given by the IS code to restrict the deflection? Restriction of maximum deflection is due to which column of your IS code and which criteria of the limit state? Limit state of serviceability, and what is the IS code saying? See page number 37 for different condition of support. Okay, according to that, we have the IS code has given some rule according to the span by depth ratio. Okay, the effective span by depth ratio. This span by depth ratio for different support condition. What are the support condition? According to the support condition, in how many ways we can distribute the structure? Generally, the basic thing. What is your cantilever? Simply supported and continuous. Okay, so this for cantilever, the span by depth ratio is given as 7. For simply supported, the span by depth ratio is given as 20. For continuous, the span by depth ratio is given as 26. All of you know this. Okay, and this is both applicable for your beam as well as slab. Okay, this criteria is both applicable for your beam or slab. So it means what? That we can get this effective length, suppose L effective by B for any simply supported beam that is given 20 means from here we can get the limited depth of this by dividing with the factor 20. Okay, means and this is for how much span? This criteria is suitable for span up to 10 meter. Okay, for span up to 10 meter, this criteria is valid. Okay, so if we have a span of 10 meters, means in 10 mm how much? 10,000. So what is the limiting depth that is coming? The maximum depth we can have. The maximum that according to IS code 500 mm. Now what if this span is more than 10 mm? For this, the IS code is saying that we can have the factor, this factor can be multiplied with 10 by span. Okay. For span more than 10 meter, we have to multiply. Suppose this factor, suppose let it be 1. Okay, so we can have the IS code is saying that this factor can be multiplied with the span 10 by span, and the span should be taken in meters. Okay, this y value turns as 10 by span. So suppose if I have a condition for suppose continuous beam, we have of span 12 meter. Of 12 meter span, what will be the maximum? Depth. What is the maximum depth? Can you find out? For 12 meter span, for normal 10 meter span, what will be the value? L effective by 26. Okay. For detail, how much it is coming? Bolo. Otherwise, bolo. Take out your calculators. For D12, how much it is coming? here what we will do? For D12, we have to multiply this with, we have to take this value as in meters, then 100 convert that into 100. Okay. So 26 into 10 by 12. Okay. So that is why I have mentioned that we cannot take as mm value. Okay. You have to be careful about that. If you take this as mm value, it's an absurd value will come. Okay. Ultimately the value will come in terms of meter, then you have to convert that into meters. Okay, how much this value is coming? If the span is 12, 0.55 meter means 550 mm. Okay, now you can see the difference. For 10 mm span it was 461 mm or 460 mm roughly. And when we are increasing the span, the overall span by 2 meters, the depth is coming for your continuous slab, it is coming as 550 mm. Okay. All you have understood this? The criteria for your reinforcement. Okay, how much reinforcement need to be provided for minimum for your main reinforcement in tension, in compression. Okay, what will be the spacing of the reinforcement? That criteria is there. Okay, what will be the if the depth increases 5 mm, what will be the reinforcement required along the face, along the side of the beam or slab. Okay, that criteria is also there. Okay, so first, I will discuss about the maximum, the minimum reinforcement that is required by your slab. Okay, the minimum reinforcement is required based on the overall dimension. Okay, so the gross dimension. If we are using mild steel, then from the cross section area, the quantity of mild steel that is required is 0.15%. Okay, of the overall cross area, cross-section area of the slab. And if you are using high strength deformed bar, okay, HYSD bar, then this percentage becomes 0.12% of the gross cross-section area. Okay, why this difference is there? I have already discussed in the shear class why the requirement for the steel is more for your mild steel and lesser for your HYSD bar. Why? For obvious reasons, the mild steel, the surface is smoother. Okay, the yield stress is already lower. That is one point. But another point is that the surface is smooth for your mild steel, where in terms of HYC bar, the surface is what? Is it smooth? It is ribbed. Okay, so this rib is acting what? What is the purpose of having ribs in your HYC bar? It is acting as one of your grip. Okay, it is helping for your bond because of the uneven surface. Okay, because of the ribs. So it is acting as a grip. So that is why it acts more perfectly in tension compared to your mild steel. So that is why the requirement of percentage is lesser, 0.1% compared to your mild steel bar, 0.1%. Okay. Main bars. Okay. But what does this mean? This is the cross section of the beam. Okay. So the distance between one bar from another bar, the horizontal distance, means the spacing between the clear spacing between the bars is a requirement for in your transport. And what is the requirement? The requirement is basis for the aggregates to get inserted into your soffit of the beam. Okay, for this reason we have provided the minimum clear distance between the two primary reinforcements, whether it is for tension or compression. Okay, and the criteria is that, first criteria is that the minimum dia, the dia of the reinforcement, if all the reinforcements are equal, the dia of the reinforcement if all are equal, means if all are suppose 20 mm dia, then the minimum distance, minimum space between the primary reinforcement should be 20 mm. Okay. If the dia of the bars are equal, then we have to go for the minimum distance between the dia. If the dia are unequal of the bar, if the dia of the bars are unequal in a section, suppose there is a combination of 16 mm dia bar and 20 mm dia bar, then we will go for the maximum dia. Okay, for unequal number of dia bar, take the maximum dia of the bar. Okay, then if the combination is suppose 20 mm and 16 mm, then we will go for the 20 mm dia bar. The minimum distance between the bar is 20. Another criteria is that the nominal size of the aggregate, the nominal size of the aggregate plus 5 mm. nominal size of the aggregate criteria is coming, as I told you, that the spacing between this horizontal spacing between the paths is taken care to make sure that the aggregates, the coarse aggregates, have sufficient space to get into this, get inside this passing. It can pass through the layers of the tension reinforcement and it can reach at the bottom. And this is required for what? For perfect compaction. For perfect compaction, we need the coarse aggregate to get evenly distributed in the cross section. Okay, in every corner, in every portion, the coarse aggregate should be uniformly distributed. But what is happening, since we require more amount of tension primary reinforcement at the bottom, so there is lesser sufficient space required for the aggregate to get inserted, to get at the socket. To make sure that the sufficient space is there available for the coarse aggregate to settle near your socket, the spacing the minimum spacing should be there in the primary reinforcement. Okay, the horizontal space, and that is given, that is ensured by taking maximum amount this value. Okay, the maximum value is chosen. Okay, suppose I am giving an example. Suppose this layer is 16 mm, this layer is 20 mm, and nominal maximum size of aggregate is suppose 20 mm. Now you tell me what will be the minimum horizontal distance between the two bars. 16, 20 and 20. Now you tell me, now what is the first criteria? First criteria, the maximum, the dia of the aggregate, dia of the bar, reinforcement bar, the dia of the reinforcement bar is unequal. So first cancels out. Second option is that unequal. If it is unequal, we will go for the maximum value. So from the second criteria, we are taking as 20 mm. Okay. Now from the third criteria, what will be the value? You tell me. The nominal maximum size of the aggregate is equal as 20. So 20 plus 5 is 25. So what value should you take? So from this two, we have to take the maximum size. So 25 is the maximum size. So the answer is 25 mm. It's the nominal maximum spacing between the aggregate in the reinforcement is 20. Understood? So what like this? ठीक है? Okay, take out your IS code. Take out your IS code. Take out page number 38. What is given in page 38? You have been given me charts. Okay. This chart is between your percentage of tensile reinforcement and modification factor. Okay. So take out page number 38. You have here a chart, okay, where you can choose any modification factor that is required for the restriction of the deflection. Okay, maximum deflection of the bar. So once you have checked all the, you can take out the restriction for the maximum deflection by using what? By using spline by depth ratio. There is another mode by which you can check the deflection by checking the percentage of tensile percentage of tensile reinforcement. Okay, so there is a formula given here that to find the value of Fs, it is 0.85 into Fy into the area of the cross section of steel required by the area of cross section of steel provided. So this formula, from this you know the value of Fy 0.85 into area of the cross section of the steel required. Okay, from the previous problem that we have encountered, you can find out the area of the steel that is required, AST. Okay, so that whatever we have got to the whatever required, whatever we are providing, because whatever steel is coming, we cannot get the exact value. Okay, either we are providing sometimes more of that or less of that. So how much we are providing, how much more or less we are providing, that factor can be taken out, that modification factor can be taken out by this formula. Okay, and we have to just multiply the modification factor with this, the value of Y for your tension, for tensile reinforcement. Can we find out L by D into the modification factor, the value that whatever it has come, that we can find out. Okay. From here we can find out what should be the maximum depth of the beam or slab according to the tensile reinforcement that is designed. Okay, this is one of the check you can see. Understood? Next, we'll go to next page, page number 39. Go to page number 39, next chart, that is figure number 5. This figure. Modification factor for your compression reinforcement. Just let me briefly describe how to see the modification factor. Not only the tension reinforcement, for compression reinforcement you can also find the modification factor. This modification factor you get the Y value by multiplying the modification factor of tension and compression. Okay, you will get the compression reinforcement that you have taken, that percentage, and how much modification factor is coming based on the percentage of the compression reinforcement that you have taken, that you have chosen. Okay, from that you will get the corresponding curve of your modification factor that you have to put, and from there you will get the minimum depth. Okay, the minimum depth you will get. Next, figure number 6 you have. In that figure, you are getting another chart where for your flexed beam, we are having reduction factor. This is the modification factor. For next beam, we have reduction factor. Why we are taking the reduction factor for next beam? You see, suppose we have this one, this is your normal rectangular beam, and the flange beam is what? There is wave and flange, right? So the quantity of this area, when we compare, this area is getting neglected. Since for L by D ratio that we are taking as a percentage, for suppose simply supported beam we are taking by factor is not starting from 1, it will actually won't start from 1. It will factor affect from 0.8.